So, okay, I am an instrument scientist for FIFI LS, and I will talk you about something that it's important when you do spectroscopic observations with SOFIA, and actually it's not a problem when you do observation from space, which is the effect of the atmosphere. When I was at university, I had a professor of algebra that started his classes like that. He says, "Don't be scared about what I'm going to say, because if you remember, when you're in elementary school, you started with strange words in mathematics like parallelogram, trapezoid, whatever, and you are not scared. So don't be scared now." So I remembering this, I thought, okay, I'll call this talk Telluric absorption. But what Telluric means? So I went to search, and Telluric actually comes from Latin. It's actually Tellus was a goddess of the earth, like sort of Mother Earth. And this means that Telluric has been used like things related to Earth. In this case of spectra, if you're looking to stars or galaxies, you'll get their light, so they're all their lines in emission absorption, but you'll get also something that's related to Earth, so the effect of the atmosphere. So that's why tellurics come from. Okay. Okay, now it's interesting because I cannot access anything.
Hey Dario, would you like me to share your slides?
Have you tried on your keyboard arrow?
Yes, I tried, and everything goes. Let me see. Stop sharing a moment. For some reasons, when I share, I cannot progress. Very interesting. Okay, that's going to be very uncomfortable.
So Tubbs is sharing your slides now. Is that okay?
I actually modified the slides, so
Oh, okay.
I can show my slide is better.
Okay.
See. Stop sharing. Start sharing. Okay. So can you see them now? It's very weird because I was not able to progress. No, now I can. Okay. That's the typical reason why you are observing with the SOFIA, and that's probably stuff that you saw at the beginning of the talks. And when we try to observe in the far infrared from the ground, and for ground means any observatory on Earth, also high as Mauna Kea, we see that the wavelength range discovered by FIFI LS, which is between 50 and 200 microns, is completely opaque. If we go in the stratosphere, we can finally observe, but there are still many lines that are due to the atmosphere, so the famous telluric lines. What are these lines? There are lines that come from different gases that are still in the atmosphere. So here you can see what our atmosphere is. We have a first layer, which is called the troposphere, and the troposphere is where we have essentially all the meteorological effects. And this part contains most of the water vapor in the atmosphere. So here you see the temperature. The temperature plummets as you go up until you reach a kind of a discontinuity called the tropopause, where the temperature stays more or less constant. The layer that comes after the troposphere is the stratosphere, which is essentially a much calmer place, which has a kind of more constant temperature and has almost no other vapor. So it's still like around 1% of the water vapor contained in all the atmosphere, but much less. So it opens our view of the far infrared. But still we are essentially inside or over us there is the ozone layer, so we still have emission from the ozone and also other gases, but these are the two main things that we have. So SOFIA typically flies between these two altitudes, between 38 and 44,000 feet, which correspond more or less to these values in kilometers. And essentially, it allows you to overcome this problem, at least most of the problem. Now, what happens really in the stratosphere? The stratosphere is not a fixed stratus because it changes depending on two things. One is the latitude. So if you go at higher latitude, so toward the pole, the stratosphere actually, let's say the altitude at the tropopoles is much lower. And if you go toward the equator, it becomes much higher. Not only, but sometimes there are some big tempests, thunderstorms, and some water from the troposphere actually start to go through the stratosphere. So that's typically happen when there are tornadoes and stuff like that. And we fly actually with SOFIA, and we have to avoid these turbulences. Here you see the location of the two airports where typically SOFIA flies. Palmdale is on the right, which is around, I think, 35 north in latitude. And you can see that as we go up, and this is the band where SOFIA flies, we are actually in the stratosphere. But typically we tend to fly north, so fly toward Canada. And we fly up to typically 60 north. Where we go from the southern hemisphere, and this happened in the past, going from Christchurch in New Zealand, and more recently from Tahiti, and in the near future from Chile, we go in this zone, and we go toward the southern pole. The other things that change the altitude of the tropopoles is the season. So here I put a very complicated plot, which shows on the x-axis, the altitude in thousands of feet. So the typical altitude that you go with SOFIA. And here you see the precipitated water vapor, which is essentially the value that we measure the vapor. So whatever is the column higher than us that contains all this water vapor. And we see that I divided this observation in two sets, one from April to September, which I call summer, and one to October to March, which I call winter. As you can see, every one of these has the histogram of the water vapor during the observations. And we can see that in general, as we go to a higher altitude, the precipitated water vapor goes down. But when you are in summer, the values are more scattered than what is in winter. In winter, we are much better off. Okay, so there are ways to essentially take care of this water vapor or lines of absorption. And these are models of the atmosphere that are available publicly. The one that FIFI LS uses nowadays is the ETRAN, which has been developed by Stephen Lord in 1992, and is available. So you have a report available, a website where you can actually compute values of the absorption. Another one that is used, I think, from GREAT, for instance, is the AM, which is completely available online, and you can find here. But the problem with AM is that you actually need to feed it with a model of the atmosphere. So how many layers you consider, what you use, it's in the different layers. ATRAN is much more simple to use because essentially already makes some assumption for you. When FIFI LS flies, we observe we try to estimate the water vapor in the atmosphere for every change of leg. So typically, FIFI LS observe different objects during flight, and when we change object or target, or we change altitude, we take an estimation of the water vapor. How do we do this? We observe simply the atmosphere in some particular lines, and these are the lines you can see here. And we try to fit the ATRA models by, of course, putting the ATRA model at the altitude of the observation and varying the water vapor values. So you can see here that the best fit is around this value, and in this case was 3.26. And this is the fit that we do of the feature that we have observed. And At the end, what we do is to consider the entire flight, and you can see here on the right top hand the path of the flight as a function of the altitude. As you can see, when we start, we are like we start observations. We are around 39,000. Then we go on, and we go as we go on with the observation. We consume more and more fuel, so we can go up and up in the atmosphere, and we finish it much higher. And then we can go and we land back to Palm Day where we start. There is one website maintained by the European Union, which is the Copernicus site, which contains data from all of the satellites that observe the atmosphere, and merge them to obtain several values pertaining to the atmosphere as a function of time, altitude, and geographical location. And we use this site to compute the water vapor observed from the satellite along the path of SOFIA during each flight. Then we use our values to rescale these values observed by the satellites and correct the spectra. So in this case, you can see that the flight, which we call 640, which is being flown last year, here we have the different values observed of the water vapor, and we anchor the values from the satellite to these ones to obtain all the values of water vapor during the observation that we apply before the reduction to every single frame we observed with FIFI LS. Okay, so if you go in the archive, you can actually recover all the raw files that contain these values. So what we do for every single of these files, single one of these files, we add to the header a value which is called WVZ, which stands for water vapor zenithal observed, OBS. And you can find this value. In the header, there are other values related to the water vapor, which can be confusing, so I'll say just don't consider them. These are values from the water vapor monitor that is on SOFIA, which unfortunately never worked perfectly. So we are now not considering, but they are still contained in the header. So sometimes they give really weird values. They go completely to zero, or in this case, they have huge values that actually you cannot find in the stratosphere. So this is the values that there are. So if you grab some data from the archive, you can check in the header, and I usually use this command which Python has, so the fifth header, and I grab the WVZ to find out if these values are defined. We are now completing all the old data with these values. So we are adding values to data where even when we're not doing this observation of water vapor, because we are using essentially these satellite vapors, satellite water vapors values, and we are using a kind of a median rescaling that we found in many of our observations. So this is almost completed. So very, very soon we'll have the entire archive will contain water vapor values for each one of the observations. So this leads directly to the fact that the pipeline to reduce the data of FIFI LS is publicly available, and you can see here the links. And I think Ariel put the link also on the useful link that she gave for the school. And this pipeline can be, if you have Python Anaconda on your computer, can be easily installed with this command, essentially getting conda install and giving the SOFIA Redux as file. Another thing to do once you observe when you download the pipeline, you have to download also all the grid or ATRAM models that we computed. And this is contained also on the same GitHub. We have to say that ATRA is not perfect. So there were a few lines that in the ATRA models are overestimated. So what I did was correcting these models following what we observe. So these lines are no more in these grids. But if you grab directly the Atran models from the website, you will still have them. So I advise you to get what I conserve in this repository. So I went too fast. So once you have the pipeline installed, you can simply do, okay, there is a GUI that I'm not going to show, but there is a tutorial online how to use the GUI. Or you can simply use a command line, which is what I usually do. And essentially you do this kind of command where the last file gives you all the files that you consider for the reduction. And the first file is a configuration file. The configuration file contains many things, but for the water vapor, it's important only to consider this set of parameters that I put here, where it says essentially use water vapor. True means use the water vapor that is observed. And this Atran here is the path where you can find the water vapor mode, the Atran models that you downloaded. So you have to put somewhere and add this one to the water vapor. The cutoff is a value of water vapor where you can decide to not apply the correction. So if you go in, for instance, in this case, if you think that the transmission 0.4, it's more than enough for you, you just put 0.4. Usually in the pipeline, I think it's 0.6 to be more conservative. Okay, at this point, you want to see what you get. And I developed a program to see the spectra of FIFI LS in a kind of user-friendly mode, which is called SOSPEX. You can get it directly from my GitHub site. And you can install with Anaconda Python also. You can find all the instructions on this link. This one, once you have a cube made by the pipeline, which you can also get from the archive, by the way, allows you to easily see it in 2 dimensions. So in one side, you have the part which is essentially the image that you have at one wavelength, and the other side, you have the spectra that you have in 1 pixel. So in this case, you put a pixel here, you get the spectrum. In this case, you put your cursor here, and you get what is the image in this part of the cube. The spectral part has many curves, as you can see, and the main curves are the red one, which is the atmospheric transmission, and you can see the scope between 0 and 1. Then we have the green one, which is the spectrum which has been not corrected for atmospheric transmission, and the blue one, which is the one corrected. So you can see in this case, we have the line of 01 at 63, which is highly affected, unfortunately, by one water vapor feature. And in this case, it becomes very important to make some correction, but also not to overcorrect. So in this case, we have simple continuum. And the continuum is easy to correct. So you can see in this case, it's practically a perfect match. So we see that the transmission and the observed flux are more or less the same. So the correction will be almost perfect. So we have just something like that, like a line.
Dario, do you think you can wrap up soon? Because we're eating into the break. Awesome. Thank you.
Sorry. And in the case of a line, we have something that is, in this case, slightly overcorrect. So you see, this is what we observe. But if you correct like that, we overcorrect. Why this happens? This happens because actually the correction made is with a curve that is essentially the atmospheric transmission convolved with the instrumental resolution. So this means that if the line is unresolved, actually we will not have any flux here, but the flux is just here because of the instrumental effect of the convolution with instrumental resolution. So we are actually adding flux. In this case, what I advise for a simple solution is just to use a tool that I put to recompute the flux with atmospheric transmission and the reference wavelengths. This will make a better choice. In SOSPEC, you can also use some different atmospheric transmission just to see what you get. And here you have some reference papers that you can consult to see more about these effects. And since someone asked for advices, I put some advices that I can probably give to people studying. And that will be all. Thank you.